Hey guys, welcome back. We'll continue with the book Cracking Codes with Python, and in this video we are going to cover the public key cipher. All the different encryption methods we covered so far always use the same key for encrypting and decrypting a message. And that of course poses a problem because it can be difficult to share the key to decrypt the message without it being intercepted. The public key cipher works differently. It instead uses a different key for encryption, the public key, and for decryption, the private key.
Let's cover how public key cryptography works. The challenge that we faced so far is that if we want to communicate securely with another person, we needed to give the other person the secret key. But that can be very difficult because if you want to send that secret key using email, for instance, it could be intercepted by somebody else, and therefore it's not securely transmitted. Public key cryptography solves that problem by using two separate keys. One key for encryption and one for decryption. To encrypt the message, we are going to use a public key, which can only be decrypted using the decryption key, which is the private key. So each person is holding on to their private key, but the public key can be exchanged. So we could send, for example, an email and include the public key. And even if the public key is intercepted, it's not possible to decrypt the message unless the user has the private key as well. And the public key cipher can not only be used to encrypt and decrypt the messages, but it can also be used for digital signatures. We need to be aware though of one important fact, that there can be a man-in-the-middle attack. So if we send an unencrypted message with a public key, it might be possible that someone in the middle is intercepting it, and the person could then replace the public key with his own public key and forward it to the other person. And this way, a person in the middle would be able to read all the messages because the two parties involved are encrypting messages using the public key that is generated by the person in the middle. So therefore we need to make sure that we actually know who we are communicating with, which is the challenge of authentication. Now in order to generate the public and the private key, we're going to follow a three-step approach. We are first going to create two random, different and very large prime numbers, P and Q, and then we're going to multiply these two numbers to get a number n. Then we're going to create a random number, E, which is relatively prime to P-1 times Q-1. And then we're going to calculate the modular inverse of E, which we can call D. So let's open up idle to create a program to generate our private and public key. We can start out by creating a new file, which we can call makepublicprivatekeys.py. In order to generate our public and private key, we are going to import the random module as well as the sysOS primenum module, which we wrote in the last episode, and also the cryptomath module. We then have our main function. We start out by printing making key files, and we are going to call a function called makeKeyFiles, which we define further down, and we pass two arguments to it, a string and the number of bits for our key, in this case 1024. And finally we are going to print out key files made. Now to generate our key, we have two numbers, P and Q, which are initially set to 0. And then we are starting out with the three steps we just talked about. So we are going to start by creating two large prime numbers, P and Q. And we are making sure that they're not the same. So here we are checking while P is not equal to Q. We are going to use the primenum module we created in the last video. And we are calling generate large prime, passing the key size as an argument and storing that in P. And we do the same for Q. And if P and Q are different, we're then going to generate the number n by multiplying the two prime numbers. In the next step, we are going to create a number E, which is relatively prime to P-1 times Q-1. And we're not going to go into why this has to be the case, but it basically ensures that E will always result in a unique ciphertext. So we're having a while loop that is set to true, and then we keep trying random numbers for E until we found a prime number which is relatively prime according to these conditions here. So we are using the random module we're calling randrange, passing 2 to the power of the key size -1 to it as the lower range, and then 2 to the power of the key size as the upper range. And then we are calling the GCD function, which is part of the cryptomath module, passing the number E as an argument, and then also P-1 times Q-1, and we want to make sure that the greatest common divisor between those two digits is 1, because then we know they're relatively prime. And if that's the case, we're going to break out of our while loop. In the final step, we are going to calculate the number D, which is the modular inverse of E. So here we are calling find modular inverse, a function defined inside of the cryptomath module, passing again e and p-1 times q-1 as arguments to it. And then we are defining our public key as a tuple consisting of the number n and the number e, and the private key consisting of the tuple of n and d. And then we're going to print out the public key as well as the private key, and we are going to return both values as a tuple. Now we're using this generate key function inside of our make key files function, which accepts the name and the key size. And this function is going to create two separate files for the public key and the private key, both of which are text files. And we are starting out with a safety check to make sure that we are not overwriting our old key files. After that, we are calling generate key, and we are storing the return value, which of course is the public key and the private key, back in two variables, public key and private key. And then we are writing our public key to a file and also our private key to a file. And at the end, of course, we are closing the two files. So let's see the program in action by actually running the module. And here we can see that we are generating those numbers. And here we can see the public key, which consists of a tuple of two separate numbers. Our first number up here, and then the second number. And the private key as well consists of two numbers. The first number n, which is identical to the public key, and then the number d, which of course is different from the second number from the public key. And then we can see that the public key has 607 digits for the first number and 309 digits for the second number. And for the private key, the first number of course also has 607 digits because it's the same as for the public key, but the second number has then 616 digits. And then both the private key and the public key are of course also generated as text files, and those text files can then be used. Let's have a look at the practice questions. The first question is, what is the difference between a symmetric cipher and an asymmetric cipher? So for the symmetric cipher, the key for encryption and decryption is always the same. And that was the case for all the ciphers we looked at so far. An asymmetric cipher, on the other hand, is a cipher for which a different key is used for encrypting and decrypting a message. An example of that would be the public key cipher that we're working with in this episode. Second question, Alice generates a public key and a private key. Unfortunately, she later loses her private key. Will other people be able to send her encrypted messages? Since Alice generated the public key, other users will be able to send her encrypted messages. Will she be able to decrypt messages previously sent to her? That's no longer possible because she doesn't have a private key anymore, which would be required for decrypting messages which have been sent to her. Will she be able to digitally sign documents? That's also not possible anymore because for that she would also need the private key. Will other people be able to verify her previously signed documents? That is possible. Other people can verify her previously signed documents using the public key, which she signed when she still had access to her private key. What are authentication and confidentiality? How are they different? So authentication is verifying that it's actually the person they pretend to be, so that nobody else is sending a message pretending to be somebody else. Confidentiality, on the other hand, is keeping the information secret and readable only by the intended person. And finally, what is non-repudiation? So non-repudiation is a property of signing a digital message so that the person later cannot claim that they didn't verify a certain message.
We covered how public key cryptography works and how we can work with a separate private key and public key. In the next video, we're going to put that into action to encrypt and decrypt our messages. Feel free to subscribe to the channel to not miss any videos, and see you guys in the next video.